very interested in. Okay, so let's talk about what we talked about yesterday. So yesterday we talked about the basics of Kubernetes, right? What Kubernetes is, the amazingness of container orchestration and how Kubernetes has pretty much dominated the landscape and how it's, proffered by the CNCF. We then talked about the different components like the data plane and the control plane, how the master nodes or leader nodes are on one side and the worker nodes are on the other, and how the basic unit of work is pods, right? So we talked about that. So containers go into pods, and that's basically how things are deployed. We then started peeling back like how namespaces were virtual cordons or slices of a cluster, and that there was no limiting the application of a namespace. When you create a namespace, the entire cluster participates in that namespace, which means that pods can be deployed into namespaces across the entire cluster. That includes the masters. Although just to say this, none of the applications that you deploy will by default be deployed into the master nodes. The only thing that ever gets deployed there are the components for Kubernetes. We also mentioned that a cluster is just a collection of machines, can be physical or virtual boxes, but mainly a cluster just has a single purpose, in this case, container orchestration. Then we talked about worker nodes, right? And that could be Windows or Linux. We talked about master nodes, which can only be Linux at this point in time, and that the predominant discussion around like container orchestration is going to be around Linux because Windows needs some work. We did talk about pods and how they are pretty much the underpinning of every single workload type inside Kubernetes, with rare exception. And that, you want to group containers into pods based on how you want to scale your applications. If you want independent scaling, you do not stick your containers together into a pod. If you want group scaling, then you stick it all in the same pod. We talked about how labeling or tagging is actually essential to managing both your nodes, your scheduling, and your deployment of pods across your environment. We talked about different tags like Linux versus Windows, no GPU versus GPU, bad actor versus just normal. There's a couple of different ways to apply tags to control the scheduling. And then a little bit about label syntax, which, you could use a prefix, which is a fully qualified domain name, plus up to 253 characters, for your actual domain name, and then 63 characters for the actual key value. So for example, it could be, storage.kubernetes.io, which can be up to 253 characters, /storage, which can be up to 63 characters, right? Values, by the way, have the same restrictions. They have to be the same length as names, which is 63 characters as well. Very limited as far as like the special characters you can use, which is basically dots, dashes, and underscores. Okay. Annotations we mentioned were like labels, except that they're really just to store arbitrary metadata. They're not even really read or used, but they can be read and used if you want them to be. And they didn't have restrictions on like sizes and character types. The label selector was what you could use when running the kubectl command, or just when you're using the dashboard or in YAML, where you can basically say, look, I only want to run my application where the node is tagged as a web server, or like role equals web server, or environment equals production, or GPU present equals true. So you can use the label selector to control where your pods are going to go based on operating system or any other tags that you have set in the system. And then we talked about like the existence of replica sets, which are created for the various workload types. And the replica set's job is to actually make sure the number of replicas you asked for is running, not more, not less. So if you ask for 5, you get 5. 1 drops, it adds 1. You add 1, it deletes it, right? So keep it at 5. So, and that you can turn the dial on your replica count if you want to, but the replica set is what controls that. And that's an object inside Kubernetes that gets created for you automatically when you deploy any of the 5 workload types. This is really only used, by the way, with deployments, stateful sets, and daemon sets. And really it's stateful sets and deployments that this is mainly used for. And then we talked just superficially about the existence of load balancers. They're mainly called services. And we talked about external name as one of the service types, because that way you could do a redirection to an external DNS name. But that cluster IP, node port, and load balancer are also different types of services. we mentioned this verbally, is that ingresses are another type in a sense of service that allows you to do resolution based on name instead of based on IP address. So you can send actual multiple names like rancher.localdev or, elasticsearch.localdev to an ingress service, which is very different from a standard service. And that ingress would actually redirect to different pods based on the name you submitted. So think of this as the same thing as name resolution when you're running like in an Nginx or Apache web server, is that instead of resolving based on IP address, ingresses, which is separate from services, will resolve on name when submitted. Services will typically resolve based on IP address, although you can also use DNS. We mentioned that containers inside pods are already ephemeral because that's just the way Docker rolls. If you want to make any container / pod permanent because it's got a database or data that you really want to keep, you've got to add a storage volume to it. And that's true at the Docker level, which are called volumes, and true at the Kubernetes level, where they're called persistent volumes. Secrets and config maps, which config maps aren't listed here, but the difference between secrets and config maps is basically one stores sensitive information and the other just stores like plain text configuration information. Secrets can be encrypted, but by default, they're just base64 encoded. Both config maps and secrets can be mounted into containers inside pods as either environment variables or as part of your file system inside the container. Secrets and config maps are used to pass configuration information or authentication information directly to applications that are inside of a container. So this way, you can actually plop a container down in 3 different environments, prod, QA, and dev, and it might get different database credentials, even though it's the same application with the same kind of internal image configuration. So this way, you can actually make the environment control the application, and the application doesn't have to do all this coding and self-awareness and other things to understand whether or not it's in prod, dev, or QA. Resource quotas, which are highly recommended. Every time I throw a YAML file, by the way, in Visual Studio Code, and I don't have resource limits, it's the one thing Visual Studio Code complains about every single time. It's like, hey, your pod specification doesn't have any resource limits. Are you sure you want to do this? Resource quotas allow you to limit the size of a pod, right? And subsequently containers based on the memory footprint and the CPU utilization. You can actually add different third parties that can also control network utilization, but by default, Kubernetes does memory and it does CPU. By the way, when you set resource quotas, you can actually set like, this is what I want to start with, and then you can set what your maximums are. But if you don't put limits on a pod and the container inside, the application inside grows, it's going to eat as much space, memory, CPU as available on the system. So something to be aware of. Authentication and authorization, right? We talked about either tokens, passwords, and certificates, which can either be based on roles, attributes, or you can federate with a third party. We talked about how Kubernetes doesn't really have the idea of users. It uses certificates to generate users, right? Which is why when you run kubectl, your kube config has to have a reference to some kind of certificate because it uses certificates to identify users. Then we touched a little bit on networking, but basically what we called out is that, every single pod gets its own IP address because they're treated like virtual machines. And then what ends up happening is that when you have to route to another host, all those IP addresses are advertised from one host to the next. So Kubernetes knows where everything is at, or it can talk to the etcd database to find things. So Kubernetes, one node in the cluster has the ability to find out information about any other pod, node, or object in the cluster if necessary. And then we talked about the Docker registry because as you run, like, for example, Kubernetes across all these systems, it's got to download a container image from a third party. That can either be on the internet or it can be a server inside your data center. So it's just up to you. Whenever we use Docker build to create an image, we can push that image to a repository, and then Kubernetes can download that in mass. So it can download it at volume and at scale. And that was our summary from chapter 1 yesterday. Just like a quick high-level skim of the existence of these various objects inside Kubernetes. Any questions thus far? Spark any questions? Okay. Then we talked a little bit about Kubernetes architecture. We got a little deeper here and talked about the various components. Some of this we had already talked about as far as like master nodes and their pieces, the controller manager. What happened is that we started talking about the existence of things like the API server, the controller manager, the cloud controller manager for AWS, the cloud controller manager for Azure. And we talked about the scheduler and etcd. These are all components that sit on top of your master nodes. The controller manager we talked about as being basically the thing that's responsible for making sure all the components are assembled up and healthy. And then we talked about nodes as being where all the applications are being run. Other components that make me sense here are obviously the fact that pods are the base unit of deployment, and containers are inside of that. Now, when we interact with Kubernetes, we're actually talking to the API server, which everything talks to the API server in Kubernetes. So almost nothing talks directly to anything else. It all routes to the API server, whose job it is to translate calls from, say, like the scheduler out to the etcd database. So it acts as a translation medium for anything that's shoved into the system, which is what the API server is supposed to do. The other thing to mention is that there is a scheduler obviously there, which is responsible for distribution and scheduling of pods across the entire system. And then the only other thing is that on the nodes themselves, there's this thing called the kubelet and the thing called kubeproxy, two pieces of software that actually interact with Kubernetes, and the kubeproxy's job is to control networking on each of the individual worker nodes. And then we moved on to build. So after we kind of set the foundation of pretty much what we're talking about for the next 2 days, 3 days, we then went on to talk about how Docker is like a brand name for containerization. But what a great company, because they gave basically containerization to the world, and now it's taking it by storm, right? And that how containerization is really just process virtualization. You're not really virtualizing an operating system because there's no kernel here. And then you could run Docker on any 64-bit Linux distribution that's old, has a 3.10.0 or older kernel, and that Windows server 2019 can also be used, right, to host applications, containers. Remember, Windows containerization, depending on what mode you choose, can be very different. So you've got to pay attention, because it is not the same. And a lot of your tools will work the same. Some of them won't. So you just got to pay attention to that. Let's see. There was also mentioned that this is a re-leveraging of an old technology that, BSD had, and then it was passed over to Linux, and then it showed up in Sun Microsystems, and then Docker really made it easy to use, right? So think of it as the evolution of like, hey, we really used to love taxis, which I actually think taxis are still pretty cool. But once we started using Uber and Lyft and all those guys, we were like, I'm not really using taxis anymore. And so same thing. It's not like the concept of ride sharing didn't exist before, but Docker made it easy, just like Uber made it easy. And Uber is not a great company from my perspective, culturally at least, but Docker is really awesome. Note that we talked about how all of these abstraction layers were introduced between Docker and like the administration of containers. And Docker created, these open container initiatives, these like container runtime interfaces that are super standardized, so that the world could enjoy containers with some level of standardization, instead of people just coming up with their own definition of containerization. They gave that to the world, in particular to the CNCF, which then now is the standard by which almost every container provider actually adheres to. So that way they can run on Kubernetes or a Linux kernel or whatnot. Now, to containerize an application was just as simple as building your app, generating an artifact, copying that artifact into the actual container file system, making sure that container file system also contains your supporting libraries, and then executing that application inside the container. Now, a Docker file with a capital D is what Docker uses, not Builder, not Podman, not any of the other tools, but Docker in particular uses this file to create an imperative set of instructions for where to source your base image, making directories, running commands, doing copies, like exposing ports, and then with command and or entry point, you can specify what you want to execute at the end. Remember from our earlier discussion, command offers a lot, like one more step less of flexibility if you want to overwrite what's being called at the end of the file. Entry point requires you to add a flag to explicitly override the command. Okay. Environment variables, right, can be defined, right, with the env statement. So, and between env and arg, right, which is another arg like thing that you can do. One difference, by the way, is that when you set an environment variable, it's actually going to show up outside the application. With arg, it's not going to show up really outside the application. So, that is actually one distinction between the two. But for the most part, everyone uses env. You don't find a whole lot of people using arg. We then talked about how you have multi-stage builds, and you can actually alias those multi-stage builds by putting an as and then your alias, like as builder, as you can see in this particular case. And so then you can use that by like pulling down tools to build your application. And then you can actually run through stages up to a certain point or control how far you go in a Docker file by labeling your different stages. Here's another example of multi-stage builds, because one of the things they said is that if you don't actually put an alias for your stages inside your Docker file, it starts at 0, goes to 1, 2, 3, etc. Right? And you can actually say when you build that you only want to target a certain level. So here you could say I only want to target 3 because I don't want to do 4 and 5. You could say I want to target 5 because I want to go all the way. You could say I only want to target 1. Or you could use aliases like builder, stage 1, stage 2, stage 3, whatever you want to do there. The run command is the most commonly used command inside a Docker file because it says run this non-interactive command. And most people actually just run the command. They don't put parentheses around it with commas. Compare that with CMD and entry point, where it is asked that you actually put double quotes and commas around everything. So distinctions as far as style goes, right? And then expose is used to specify what port is going to be kind of exposed into the edge of the container. Remember, your application still has to listen on that port, but this punches a hole in the container and allows it to be listened to, right? Docker will send traffic to it at that point in time. You can specify those ports obviously on the command line as well, or you can put them inside your file. The copy command was used basically to copy files. Notice that there's also the add command, which pretty much does the same thing. So there's 2 directives for that. I don't know why. And then also that the command instructions had 3 forms, which the executable form is actually the one that people want the most. You can also, by the way, use the command form to actually pass parameters down to entry point if you want to. I don't see people do that a lot, just to be frank about it. And then with entry point, right, same thing, right? Entry point will allow you to be overridden, but not as easily as command will. So command just requires you to stick it at the end of your Docker run file. You can actually see right here where they're adding the Docker entry point command in order to overwrite the entry point value inside the Docker file. So, by the way, whoever's last is who's going to get run, but entry point usually trumps commands, just to specify that, right? So something to be aware of. Volume, when you're inside of a Docker file, will allow you to specify a volume. Reminder that this is not how you do it if you are actually using Kubernetes. This is really just for Docker. And that, Docker used to support a wide range of like volume types like NFS and whatnot. And actually it still does in some cases, but it no longer has the progressive kind of volume drivers like Kubernetes does because people are running Kubernetes in production, not Docker. And then you use Docker build or Docker build -t in your tag name with a period at the end that says the Docker file is right here. If you want to specify the path to the Docker file, notice it says Docker build -f path to Docker file. I don't think you need the dot at the end, actually, if you specify the path. I don't think that's required, actually. I think they just left that in on accident. Notice that the top one, the -t, is actually tagging. By the way, you can always do Docker tag if you want to tag it after you uploaded it or after you created it. And then you can use Docker images to see the image in your local image cache, much like a clone of a Git repo, right? So you can see it there. And then remember, if you have a Docker ignore file in that directory where you run the Docker file, it's going to exclude those files if you do a copy or an add command. So if you need to protect sensitive information, make sure it's in your Docker ignore file. Best practices are to be very specific about the version of where you're sourcing your image files. Make sure you do a user, even if you have to create it inside. Make sure you set a working directory as well. Make sure you do some kind of verification against downloads. Yeah. So notice it says from Debian and that SHA, and then after that hash, it should be this. What this means is that if that hash doesn't match what you're downloaded, it's going to throw an error and stop. So you can actually put hash verification as the very first line to make sure you are downloading an unmodified, unchanged image file. You can publish ports with -p, which can go UDP or TCP, right? And you can specify which interface you want to listen on. Like, so if you have like 5 IP addresses, you can specify which one. But these were all like published ports. And of course, just to mention that the Docker documentation is really good. I think the Kubernetes documentation is even better, but they're both decent, easy to read. I think Docker could use more examples, but Kubernetes has a lot of great examples in it. And then we mentioned the Docker registry, hub.docker.com, which is the most famous registry in the world, and how we would want to, would love to leverage that, but most of us use an internal registry, which then goes and pulls from the public and scans everything and makes sure it's legitimate. So, and then if you wanted to host a local registry, here was a great example, including pulling an image down, retagging it, and then pushing it back up to your local registry. And there's just more around hosting and stopping a local registry. Here, we started to shift away from Docker and talk about the different generators that could be used to basically like imperatively create Kubernetes pods and create deployments, right? So this creates a deployment, this creates a deployment, this is going to create a deployment with just different kind of flags there, right? All around Nginx. And that was the first method where you just like do a run or create. The second method is do a create, but let's actually use a YAML file. And the third method was just let's apply that YAML file. And if we make changes to the YAML file, we'll just reapply it. And Kubernetes will do its best to put everything in the state that is declared inside the YAML file. You can also, by the way, read an entire folder if you want to of YAML files. So you can read everything at once, kind of like the way Helm does it. And then we talked about, you saw me yesterday put Ubuntu into a sleep mode for 600 seconds. And then we exec'd into an Ubuntu container with bash so that we could see what was going on and just understand that we can actually hop inside of a container to grab log files, modify applications, check on libraries. And then we talked about how if you do have a multi-container pod, by the way, you can actually specify which container you want to connect to if you're trying to like bend bash into something. But that containers in a pod have the same memory space, the same networking stacking that can actually share volumes as well. Here's a multi-container pod. right, talking about how you usually have one main application pod, and then you add operational and monitoring pods or networking pods in has sidecars with your multi-container pod. And that was section 3 that we summarized. And then, of course, just like we did last time, we did a lab where we talked about doing a Docker build, and we ran through that process. And then I don't think we covered design actually yet. No, we haven't talked about design. So that's where we stopped yesterday, was in that last section, right? That was it. That was our day. As far as
I think we started on the 5, right? I think we skipped 4, we went to 5, and we were continuing till secrets on 5.
Yeah, because I think part of this was that I was going to come back and actually talk about this, just because I wanted to make sure we covered deployment configuration first.
Oh.
Yeah, so that's why because it's weird to talk about sidecars when you haven't talked about the different workload types and how that kind of all gets set up, right? So thank you for the reminder. Let's see. So we did actually talk about volumes, and then we talked about the container file system, Docker volumes, and then Kubernetes volumes, which really we're just focused on Kubernetes volumes, so persistent volumes. And then we talked about how to define a volume specification inside the pod spec, and how like mounting volumes, if you're just using like empty dir or local storage, is easy, but it's going to get a little bit more complicated when you're going to start using storage classes and like that are more advanced and require like persistent, allocation, like persistent volumes or dynamic provisioning. Here, these were the general types, with empty dir and host path being ones that you don't really need to do anything but just ask for the volume in question or mount the local file system. Local was also the same way, but NFS and then the others required a little bit more manipulation to get working. So EBS and Azure Disk and Azure File and GCE PDs, right, persistent disks, that required you setting up a storage class, making sure that you have persistent volumes if you're pre-provisioning, or either way, making sure you have a persistent volume claim. Empty dir, by the way, was deleted the minute the pod is deleted. You're not going to retain it. And so here was how we basically specified empty dir as a volume mount inside the /cache directory. And then host path, which allows you to mount a file or directory from the actual host file system. And then, of course, local volumes, which is like a disk, a partition, or a directory. This actually usually lives under var-lib something, right? Usually var-lib containers, var-lib, right? Volumes. And then an NFS mount is you just mounting across another server. You can't really control the disk for an NFS mount because the disk size is actually determined by the other server. It's not really a storage subsystem per se. And persistent volumes are the way that we create permanence inside our pods / containers. And that in order to create a persistent volume or claim one, you actually need a persistent volume claim, which is actually required. And of course, a storage class. Now, a lot of the storage classes are defined for you if they're like local or host path. But if it's EBS or Azure Disk or Azure File, you either need to create it or you need to make Kubernetes aware that it's on cloud so it can create it for you. In order to actually create a pre-provisioned static volume, you need 4 things. Like you need 4 things for a persistent volume that's pre-created. You need a storage class, a claim, a predefined storage volume, which is a PV, right? And then you need to put that into the pod specification. If you're doing dynamic disks, all you need is the storage class, a persistent volume claim, and then you need to put it in the pod specification. That's it. When you go to claim it, obviously the system is going to create the disk for you, the persistent volume, and then associate that for you. So here we're doing a pre-provisioned, basically persistent volume. So we got the claim, we got the persistent volume itself, and then we've got the pod specification that was used to call the claim, which in turn claimed the volume. When we do this dynamically, we just specify a storage class. We still actually have to have a persistent volume claim, but then the volume claim is going to go talk to the storage, And then when we actually do the pod specification, it's going to create the storage for you on your behalf and then associate the now dynamic volume with your claim and give it to the pod. So difference there, dynamic storage doesn't require you to predefine your volumes. Then we talked about secrets. And that's where we landed yesterday, was just talking about how secrets are the underpinning mounted storage for basically sharing sensitive information either as environment variables or as files inside of a mount point inside the container. We showed basically how to create secrets either from literals or from a file name, right? Here we are creating from literals where we're literally just sticking it on the command line. And then using secrets, they basically get mounted just like volumes get mounted. So no persistent volume claims, nothing else like that. Just literally the secret creation and then the volume definition. And then we were moving on to config maps, which was our day 2 material that we're covering today. So that was a quick little speed run. Any questions about any of that?
So I have 2 questions.
Go ahead.
One, sir, when you mentioned about containers, like when you were defining like the containers, so you mentioned about process virtualization, not OS virtualization.
Right.
Sir, can you help understand a little bit better?
Yeah, absolutely. I'll do a little drawing here. All right, so let's say this is my worker node. So this is my worker node. This is actually my virtual machine that's actually running. And in that virtual machine, I've got a kernel down here, right? Because it's running Linux as an example, right? What happens is I have a little process that I want to run. And let's say that process, I'm going to take that process and I'm going to put it in a container. And so let's say I'm going to put it into a green container and I'm going to run it on top of this host because that's where Kubernetes stuck it. Inside this little container is a number of binary files like bin bash, Java, right? LS, RM, right? Like little binary files that are all running up here inside this space. Now, when this actually needs access to hardware system resources or even like manipulating disks or spaces or whatnot, what actually ends up happening is that this like particular process, it actually is going to send its system calls through a standard interface that's actually the boundary of the container. And it's going to talk to, in this case, like let's say the container D, the container runtime interface, which in turn is going to talk to the kernel. But there's actually no running kernel here for the system to talk to other than the one that's existent. And actually, I didn't want to do that. So hold on just one second. Other than the one that's existent at the pink level. So there is actually, let's say this yellow layer is the containerization supervisor, the software. This is what happens in order for it to get to the kernel in pink. There's no kernel on there. Those blue binaries that are sitting inside the container, they're actually talking to an API, like to the interface, which in turn is talking to Docker or whatever the container D supervisor is. And then it's talking to the kernel. So the container never really has direct access to the kernel. And that is the only kernel in this equation. It's actually not running a kernel. So inside that little green container, there is actually no software other than the binaries and the application. That's it. The way I found this out, by the way, is that I, like at this level, let me use an arrow to emphasize this, is that at this level, I decided that I was going to run a rel, was it rel 7? I was running a rel 7 instance. And at this level, I ran a rel 6 container. And that rel 6 container contained binaries in here that were not compatible with the rel 7 kernel. There was no compatibility. So when I went to run those binaries, it literally threw a kernel error and said rel 7 does not support these calls. And I said, why am I getting rel 7 error messages at this level when rel 7's over here? Why is the container throwing rel 7 errors? I'm using rel 6. I was like, isn't it running a kernel? And I went and looked in there, and guess what? It's not running a kernel. The kernel's down here on the host. It's not in the container. So once I saw that, like, I was like, oh, and so I went and peeled it back and talked to like the Docker captains and the Kubernetes captains on all the Slack channels. And they were like, oh yeah, no, we don't run kernels inside those containers. It's process virtualization. They're not virtual machines. It's like, if it was running a kernel, you'd have to stick the whole operating system in there. You can run containers with no operating system. How does it get away with that? I was like, oh, I guess that makes sense. I didn't understand it. This is like 4 years ago. So, you know, that's what cleared it up for me back in 2017. It was like, oh, wait, hold on. That's not, the kernel's only in the host. The kernel's not actually in the container. So all these containers that contain operating systems, if those binaries are not compatible with the kernel in question, they're not going to work. This is the reason why, by the way, you can't take a Windows container and run it on top of a Linux host. This is why you can't take a Linux container and run it on top of a Windows host, because those system calls are incompatible. So that's why it's process virtualization.
So, so maybe my confusion was with the key word virtualization. So we are saying this process virtualization because that process can be, once containerized, then it can be run anywhere on any Linux distribution where run. Is that right?
Well, that is true. And there is also actually some level of abstraction. So there is actually virtual storage and virtual networking happening inside the container, right? There is some virtualization happening. Now, is it talking to the host? Of course it is. It's not as independent as a virtual machine, but there is some abstraction there. Otherwise, how will we get an IP address attached to the container?
Yeah.
So yeah, but the difference is that a virtual machine could do all that and not be super reliant on the hypervisor. The container is super reliant on the host, right?
Yeah.
Yeah.
So on that, if you were to do an analogy, would a virtual machine be considered hardware virtualization or OS virtualization?
Actually, it's both. Actually, a virtual machine is both an virtualized hardware, and the operating system itself obviously is part of that whole virtualization process. But it's really hardware virtualization. So a virtual machine is really virtualizing the hardware, so the operating system inside can actually talk to that hardware. Gotcha. Same thing with a container. The difference is that if you make any OS calls, it goes down to the host, which a virtual machine doesn't do that. Yeah. So that's why it's just process isolation, like process virtualization.
Very good. Thanks, sir. One last question that I had was about that persistent volumes. So in my example, let us say if it is NFS, sir, what backup strategies in general, like for these persistent volumes, you recommend?
Well, that depends, right, on how important your data is and what the RPO, RTO is for the business.
Yeah.
In general, if you're using anything on a cloud provider, then you just snapshot directly with the storage vendor. You don't do it with Kubernetes.
Gotcha.
Right. So you let AWS control the storage backup. So if it's EFS or EBS, you use AWS backup or use lifecycle policies and just have it backed up to whatever the business wants.
Right.
Same with Azure, same with Google, right? They all have that capability to do some kind of snapshotting on the systems. So that's all business driven.
Gotcha. So if you're using EBS volumes, we can create the snapshots for that, I guess. How about the NFS? So NFS running, I'm assuming, I haven't used personally myself, but based on what I'm seeing that other teams are doing. So thinking NFS is running on an EC2 machine, I believe.
Interesting.
Is that right or not?
Well, if it's using EFS, it's a service, and if there's virtual machines, you can't see them.
I meant to
EFS.
say NFS.
Oh, if you're just, instead of using NFS via EFS, what if you're running NFS on EC2?
Yeah.
Well, those NFS, the volumes that serve out the NFS server are going to be on EBS. So you just back up EBS on the EC2 box.
So when we use NFS in the cloud, does it use EBS?
There's two ways that for you to use NFS, for example, in AWS.
Yeah.
You can roll your own virtual machine, install an NFS server, which has EBS volumes attached to that virtual machine, and you can serve out that data via the NFS server to other systems. But you're managing that from end to end. If you use the EFS service, you don't use any virtual machines. You just have access to the service, and that gets shared out via NFS out to everybody that you want to share it with.
I see.
If you're using EFS, there's a backup service, snapshotting service, just like with EBS, that allows you to back up EFS at whatever schedule you want. If you're rolling it on your own virtual machine, which is being fed by EBS volumes, you just snapshot those EBS volumes at your discretion.
Does NFS based persistent storage, and I'm talking about it in AWS cloud. So in AWS cloud, does NFS based persistent storage have to be EBS volumes, or it is just a file system on an EC2 machine?
Well, EC2 has two types of storage, one of which is generally asked that you're not used, and the other is that you use, right? Which has 4 different subsystems to it, which is EBS. So if you're running an EC2 virtual machine, you're using EBS. So EBS can always be snapshotted. Don't get me wrong, there's another storage type called instant storage, which nobody is supposed to use.
Nobody uses, yeah.
Right, yeah, because if it crashes, then its storage goes away. It's like empty dir, right? So,
Yeah.
but if you're using EBS, you just snapshot it. So
I see. I think that I think you really opened my eyes. I think I was in dark when we were when at work. We had there was an odd meeting which I attended in a listening mode, and I was thinking that this NFS, because I don't know much about it, I was thinking the NFS is basically localized on a particular what you call EC2 machine. But if it is using persistent storage, and EC2 at the end of the day, for persistent storage, it uses EBS volume, right?
right, yeah,
Yeah.
it has to use EBS volumes.
So NFS has to use it. NFS has to use EBS volume.
Right, NFS is just a high-level protocol. It doesn't
Yeah.
actually do any data storage. It uses whatever local file system is being created by the operating system.
Gotcha.
Yeah, but I gotta say this is that running NFS on EC2 yourself, and that might be a restriction of GovCloud, but I think EFS is actually in GovCloud. It would be way better to use EFS than it would be for you to run your own NFS server on EC2.
I think that that is what the end the goal is. It's just that a legacy moves slowly.
Yeah, well, honestly, that's most companies.
Yeah.
It's not just the government.
Thank you.
We always move.
Thank you.
Yeah.
Appreciate it.
Of course. Any other questions for anybody?
One question, going back to what you were talking about with the kernel and the config maps.
Wait, I wasn't talking about config maps, hopefully.
Oh, never mind. Maybe there's something before this slide then. With the container not being able to access its own kernel from within the container, but it's from the host. Is it so if you have a container that's using the from Ubuntu
Mhm.
image,
Right.
would it be using Ubuntu kernels in the container?
No, that's what I'm saying is that it can't. There's no kernel in the container. It's
Okay,
downloading the Ubuntu binaries, but they're just interfacing with the host kernel. Because you can't run a kernel inside of a container because there's no virtualized hardware. Like, do you know what I mean? I know there's processors and there's memory and you've got like disk and all this other stuff. But remember, you can run a container with absolutely zero operating system, which is actually no binaries in there. When you download the Ubuntu one, all you're doing is downloading the actual commands. There's no actual running kernel in there. And the reason we know
Okay.
this, by the way, is that if we don't give Ubuntu a command, what does it do when you run it without a command? It starts and then it crashes.
Oh, yeah, oh, the container, yeah, the container just doesn't do anything
It
and
just
crashes.
runs and stops, right? Yeah, because there's nothing for it to do because there's no init1 process that runs the kernel.
Okay, so if I was on a Mac computer and I installed Docker and I use the from Ubuntu, those work because I guess they share binaries with the Mac kernel.
Well, doesn't that run a virtual machine inside the system?
Oh yeah, I guess it does.
Yeah, it runs a virtual machine inside the system. So that's how Windows does it too, right? Windows starts up a virtual machine and then it runs the Linux containers inside of a virtual machine. It's a little easier with Mac
Oh,
because
okay.
even though Mac is based on BSD, it's got some Linux extensions inside of it. So some of those system calls would probably actually work natively on top of the Mac itself. But typically the Mac will run a tiny little lightweight virtual machine called boot to Docker, and then it will run the containers there.
Okay, I think that virtual machine is kind of hidden from the user because I don't remember ever thinking of like that it's using a virtual machine.
Yeah, you usually can't see it. Like, and the same thing with like if you put Docker desktop for Mac or Docker desktop for Windows, you can't see the virtual machine, but you can go in and restart it, right? You can actually go into the Docker for Mac desktop settings and restart it, change it and whatnot. But I think Docker runs natively on the Mac. So what it does is it actually just translates the system calls down through the Docker daemon because the Mac is closer to Linux than Windows is, obviously, right?
Yeah.
So, but they were running a virtual machine inside of a like booted Docker. It could have changed recently, but that is required. If the kernel cannot talk for those Linux extensions, then they are going to require a virtual machine. But I'm pretty sure that a virtual machine is still there. So I don't think the Mac
Okay.
supports every single Linux call.
I guess I never really thought of it like that because whenever I deploy containers, it's usually on like a cloud, like on AWS. I'm using EC2 Linux server anyway, so there wouldn't be any problems
Right.
to start with.
Well, and it's great that they did that because they made really lightweight Linux virtual machines that literally can run inside of a Docker. Like, it's funny, like they can put Kubernetes and Docker inside of Docker, which is kind of cool. But they've made these really lightweight virtual machines that can run like on top of like, Macs and Windows and whatnot. And they take almost like little to no resources unless you really want them to. And then that way you can run your Linux kernels without having to worry about translation, right? Because what if you were downloading Mac only Docker containers and then you're trying to kick them out to Linux OSs and the OSs don't match, so the containers don't function. So they've really solved that problem by just making everybody use Linux on the back end. And then you can deploy to Linux on the front end.
Makes sense. Thanks.
Yeah. Somewhere they really thought that through, actually. That could have been a disaster, frankly. You know what I'll do is I'll dig up the article. Actually, a buddy of mine from Red Hat actually wrote this crazy article. I think he posted it on Stack Overflow. We all use that somewhere. But I'll see if I dig it up and post it for you about how do you know that it's not using the kernel? Like, how do you know it's not running a kernel? Cool. All right. So as far as today goes, mention a few things here. As far as today goes, we're going to finish out 5, and then we're actually going to go back to 4 and finish out design, because I think design will now make a lot more sense, right? Including label selectors and understanding workloads a little bit more. And then we're gonna see how far we get as far as like security and exposing applications and troubleshooting. Honestly, will cover design and then security, and we'll save exposing applications in Kubernetes for tomorrow. Lab wise, we will actually talk about, I think, so we did like labs 1, 2, 3. And then did we do 4 yesterday? Oh no, I don't think we did actually. We didn't do 4 yesterday, right? We didn't actually create deployments and do all that stuff. Oh no, logs. Yeah, we didn't do 4 yesterday. Okay. And so, and then we're going to talk about the sidecar pattern, and then we're going to get to deploying. And then if we cover security, we'll get to lab 8, but we might actually, I'm sorry, lab 7. We might start with lab 7 tomorrow, just to give you an idea. But we'll definitely do exposing applications and troubleshooting tomorrow. If we finish early, just a reminder, I'm going to talk about a little bit about the Kubernetes certification resources. If you're looking for Kubernetes certification, which, you know, I would recommend, especially since you work for Booz. Booz is really certification happy. Plus, people love that when they go hire you for projects internally and you've got the certifications on your resume. They absolutely think that's spectacular. And then we will run through a series of Kata Coda labs and other resources like the Kubernetes Playground. And then we're still probably going to finish early. So just so you're aware, we're going to finish early on Friday. I can tell already. So at like most, it might be an hour and a half to 2 hours early. At the latest, it'll probably be an hour early. Just so you're aware, which probably is good because usually by the time we get to the end of day 3, people are pretty checked out, especially on a Friday, because you're just tired from the week and people are exhausted. So, you know, we'll cover whatever is appropriate. And if someone has questions that runs us all the way till 6, I'm more than happy to stay. But for the most part, most people are done by that time, especially since we have less than 6. Okay. Questions of any type about our schedule?
I think so. One of the questions I had, like yesterday when I was trying to work on homework 3, lab 3, I meant to say the last lab, was it 3 or 4? I can't remember. But you know, at one point when I was trying to do Docker build, I believe I followed everything, but it was complaining that the current folder does not have a pom.xml file, but it did. I was in the right directory and it is there, but for some reason it was complaining, so I couldn't basically go any beyond. So question I was trying to ask is that, is there a way, are you available to like troubleshoot?
Oh yeah.
Or respond to questions like what we may have, like
Oh yeah, absolutely. So when we actually get to the next lab, I'll add some extra time to it, and then let's like do some troubleshooting with Nod before we roll into the, you know what I mean, before you roll into the next lab and see if we can figure out what's going on.
Thank you, sir. Appreciate it.
Yeah, yeah, absolutely. Okay. Let me stop this one.